So functional programming is not just lambda function. That title is because, as you know, with Java 8, we got lambda function in Java, and people were like, I'm doing functional programming. But it's not exactly the same thing, and I'm going to explain why. So there is that thing here. Excuse me. My name is David. I'm working in France in a city called Nantes in a company called Startup Palace. And also I'm doing a PhD in software engineering. And so first thing, what is functional programming? If you check on Wikipedia, we've got something like that. Functional programming is a declarative programming paradigm. So the declarative word is really important. And also, you program with expressions. I'll come back to those two concepts a bit later, but it's really important. It's becoming more and more popular, and that's why I guess you're here. So I'll try to explain what it is and how it can change your lives as a programmer. So first of all, what is declarative? If you take declarative, the opposite word in this context would be imperative. And when we say a programming language is imperative, it means that it uses statements to change the program state. It's exactly the same concept as in Turing machines. So you've got instruction statements, and they are executed, and they change state. But with declarative programming, you express the logic of computation, so what you want to compute, without describing the control flow. It means that you separate what you want and how to obtain it. To give you a little example, if my objective today, my goal is to make a barbecue, I need to go to the supermarket and buy some stuff. If I tell one of my friends to do that, I can do the imperative way and say, just enter the supermarket, go on your left, 3 steps on your right, pick the stuff that is in front of you, etc. But with the declarative way, I just say, go and get some beers. And I don't have to manage exactly how to get that result. It's not my problem. I just express the result I want. So it's the same thing we want with programming. Also, what is lambda functions? It's the same stuff as anonymous functions. So in this example, all examples will be in JavaScript. In this example, you see the first function, my function, is a regular function, like you've got in JavaScript from the beginning. It's just add +1 to whatever you pass in, and it's a regular function. The second does exactly the same thing, but it's an anonymous function, excuse me. The difference, which is really important, is that in the second case, you are describing a value and attaching it to a variable. In the first case, you are doing both at the same time, and while in JavaScript, you got the same result, but if you take another language like C, the first would be like a structure in the language, and the second would not be possible actually in C, but you've got the value, which is function of foo, etc., and you've got the variable, which is my lambda function. The third example is actually exactly the same as the second, using the lambda, the arrow function in ECMAScript 6. It's just another notation. But it's just to show you that the arrow function name comes from here, because it makes an arrow. You've got this in many functional programming languages. So this kind of stuff, a lambda function and using functions to describe programs, comes from lambda calculus, which is, I'm not going to in the detail here, but it's an equivalent theory to the Turing machine. So it's something that allows you to describe computations. But as you can see in the example, it's more like using expressions. I'll come back to that later. So if you want to learn more about this, There is a link in the slides. I'll put a link to the slides at the end. So this presentation is quite nice because it's explaining it is explaining a lambda calculus, and at the same time showing you equivalent in JavaScript. So why do we care about all this? What is the point? The point today is like you want to learn new stuff, and learning functional programming is interesting because it's not just a new technology, it's a new way of thinking about your program. And I think it is really important to discover new ways of thinking about your program, because it helps you be better at your jobs. And you ask yourself the good questions. Another point is to write better code right now. When I mean right now, it's like tomorrow you can begin with whatever language you are using, probably. And because the concepts I'm going to explain here works in many languages, not just languages that were designed for functional programming, like you've got some example, Haskell, Scala, Erlang, but also those concepts work with other programming languages like JavaScript. So today the example will be in JavaScript because it's quite simple and lots of people knows it. But it works with other languages. So 4 concepts today. The first is referential transparency. The second is higher order functions. Then lazy evaluation, and finally immutability. I'm going to explain what it is and what it is important and how to use it in JavaScript right now. So before talking about referential transparency, I'm going to talk a bit about purity. So here is an impure function. We call it impure because, as you can see in its implementation, it's having observable side effects. This means that I'm using, either by reading or writing, other things that are not in the scope of the function because they were not passed as arguments. So in the first line, I'm reading the date, which was not passed in the functions. And in the second line, I'm like using a creepy function, launch nuke, that might have side effect on the world, but we can't really tell. We have to trust, I guess. And the third line returns the result we expect by reading the name of the function divided by 2. So with such functions, you've got side effects in it. So when you're coding it, you have to read the implementation to be convinced of what it will do, because it might do anything actually. And if you code it twice, you might not get the same result, the same effect on the world, because maybe the date will be different and the algorithm will behave differently. The opposite of that is obviously the pure function. The pure function has no side effects. And an interesting property is that it always returns the same result when given the same arguments. Which means if I called my function add5 with -4 2 times or an infinite amount of times, I'll always get the same result. Because this result only depends on the arguments I'll give to the function and nothing else. So is it OK for now? Let's continue. Referential transparency is when you can take an expression and replace it by the same something with the same value, and the behavior of the program won't change. Exactly like in physics or math, when you are using equations, you can use a variable, and also you can replace this variable by its value, and it doesn't change the conclusion on your equation. It's the same thing. Obviously, it won't be it won't be as maintainable or as pretty, or I don't know, but the result would be the same. So why is that interesting? Is that you can reason on your program as if there were equations, and this is cool because it means you can modularize your program by just by just considering small parts and putting them in a big part, and it behaves the same way, which is not the case if your functions have side effects, because you can't really compose them and expect the magic to happen. So a bit of advice here for this first part. Build your programs with pure function wherever possible, because they are predictable, reliable, and you can test it really easily, because you've got a function that result only depends on the arguments. So it's easy to test. You don't have to do mocks or stuff like that. So it's perfect to express business logic and delay the side effects to other function that must be like isolated and identified as side effects functions. So you can manipulate a lot of stuff with pure function with no danger. The only thing that could happen is your computation would be slow or would not terminate. But apart from that, you don't risk to destroy the world or your database. And so if you isolate the side effect function, because you obviously you need side effect functions, because if you don't have those, your program is basically useless. It can't communicate with the world. So you isolate them, so there is no surprises. Those are dangerous. So that's it for the first concept. You see it's like a complicated words, referential transparency, but it's actually quite simple. It's just that, as I said, it was a theoretical area before programming languages came and were able to use this. But it's like the math people gave all the names, so the names are quite awful. But okay, I promise I won't talk about applicatives today or monads or stuff like that. So the second thing is higher order functions. It's also quite simple. So you know what a function is. An higher order function is a function that either takes one or more function as its arguments, or returns a function as its result, or both. So a quick example. So the first function you see there, applied twice, takes two arguments, f and x, and it would it will apply f on f of x. So it will apply twice f on x. It's a bit useless and theoretical here, but it's just to have a simple example. So as our definition says, this function would be an higher order function because it accepts a function as a parameter. The second function is a normal function, or regular function. It just takes x and return x times 3. Okay. And so when I'm calling the first function, you see I'm passing times 3 as a parameter, as an argument. I'm not passing, I'm not applying times 3. It's important at this point. There are no brackets after 3 times 3. So it's just the function I'm passing as argument. And I'm also passing a value. And you can see in the comments, it's like, because my two functions there are pure, I can use referential transparency to put equivalent expressions underneath that would be the same. It's actually all the same values. It doesn't change the program's behavior, but it also helps you to understand how it would be evaluated. So that's quite simple. But what's the point of this? The point is to having a good separation of concerns. I don't want to mix every business logic in just one function. I want to have every function to have just one goal, one point. So then I can compose them, these simple functions, to create complex functions, and not to create the complex function from the beginning, which is by definition complex. And I'm quite stupid, so I want some methods to help me on that. So let's play a bit. It's a bit theoretical, but let's see some example real-world example. And so we'll manipulate JavaScript arrays and magical ponies, because I like ponies. So for our examples, I'll have this list. So it's called ponies. It's a list of objects, and each object describes a pony. So they have a name, they have a color, and we know if they are able to fly or not. And we want to transform this list to a list of formatted strings that would just say the name of the pony and the color. So we'll drop the information of the flying stuff, and we just want a string for each pony. So it would be exactly like that. We want to create a display pony function that, when given ponies, would return an array of strings formatted like we want. So the first approach is to use the imperative way of thinking. So we do a for loop to loop over the ponies list. And for each pony, we replace the current value by a new one calculated to be exactly like the string we want to have. And then we return the array, and that's it. It works, but I've got two problems with that. The first is that it has side effects. So if you try this and like you don't care, you call the function and you really don't care about what it would return, and then you just print out the ponies variable you just pass to the function. So you pass it to the function does the stuff, returns something you throw away, and you just watch what you gave to the function. You would see that it has changed. We'll come back on immutability a bit later, but it sure has side effect because I'm calling a function that changed something that is not in its responsibility. And the second problem I have with that is that we are mixing two behaviors. The first is how to iterate on an array, and the second is how to transform our data. If you think a bit about that, the first thing is like not relevant to your project. Actually, it's more like of a JavaScript problem, because arrays are from JavaScript. But the second is exactly like business logic. So we're mixing both. It's not really optimal. So there is another solution. We use the map function from the array API, which allow us to define a transformation function. So the second function definition, which is wrapped in the first, but we don't really care about that, called transformation, only takes one pony and return one string formatted the way we want it. And then for this part, it's just the business logic, the transformation. And then the second part, we call map on the array ponies and give it the transformation method. So the map is in charge of iterating over the array, and the transformation is in charge of transforming every element of the array. So it's cool because the iterating stuff is not in our hands anymore. It's the API of JavaScript allows to do that, so it's cool. And also, if you think about it, it's not, I believe it's not the case in JavaScript, but in other languages, if you have like a big array with thousands of entries and elements in there, and you are using the for expression, you are implicitly telling that to compute the element of index n, you have to compute the element of index n minus 1. Because you have to respect to follow an order. But with map, you only say that you don't need the other elements to transform one. So you could cut the array in 4 pieces and run each of the transformation in the 4 pieces on one core of your CPU, and then like merge them back, and you are doing parallel stuff with no cost, because by design, you know, you won't need the other elements of the array to compute one. So it's like you are more precise about what you want, so it's more readable, and the interpreter sometimes can help you and do optimization. Not in JavaScript, but also exactly the same function with lambda function, well, arrow function and template strings. So it's exactly the same, but I'm using some JavaScript features to like make it more concise and readable. So you see, I've got the result I wanted. My ponies are quite presented in the strings formatted like I wanted. But then we can follow the exploration, and there is another function which is quite famous, also in the array API, which is called filter. Filter is used to remove some of the elements of a list. And filter takes one argument, which is a function, and this function shall accept one element and return true or false. If it's true, the element would be kept in the list. If it's false, it would be thrown away. So in this example, I'm returning true if the pony cannot fly, and I'm returning false if it can fly. So I'm basically saying I just want to keep the pony that can't fly. And if I evaluate the results, I've got just one pony. It's the one that can't fly in my list, and it works. So it's the same. I could do the same with a for loop, obviously, but I would have the same problems as earlier. Funny stuff, you can also chain them, because the filter return an array and the map return an array. You can chain them. So here, I'm only keeping the flying ponies, and I'm formatting their name with the function we saw earlier. So you might have figured out that those functions are higher order functions. They are in the standard library, but you can also create yours, and it's quite useful. I have a third example of function. It's called reduce. For this, I'm going to take another example. Forget about the ponies. I've got peoples, so it's a list of the objects. People have names, people have age, and I want to compute the sum of the ages. I don't care about the name. So I could do a for loop with a temporary variable to store the age of the total age for each iteration and sum it to the current value. Well, it's exactly what I'm doing here. The reduce function takes two arguments. The first is a function that would take the first thing, we call it an accumulator, and the current value. The idea is to like call this function on every element, but we keep some state between the calls, and that state is called the accumulator. So on the first call, we need to define the value to start with. Like if you have an empty array, what should it return? So because I'm doing a sum, if there are no stuff to sum, I expect to get 0. So it's the second parameter of reduce. And then for each element, we are calling the function, the lambda function we gave to reduce, with the accumulator. In the first case, it's 0, and the current value, which would be the first object. We are then adding the accumulator and the age we extract from the object. And because we return that, it would be the next accumulator until there are no more elements in the array. And then we return the last accumulator. So this would compute the age, the sum of the ages of everyone in my list. Which is funny is that this reduce function is actually more general than map and filter, because you can implement map and filter using only reduce, which I put there. But it's not that interesting. It's just to show you that the reduce function is an higher order function, and I can specialize it by giving it some arguments that would make it more specific but still not completely defined because map still requires some arguments. So yeah, that's it. So to sum up this, my advice is avoid loops like while or for. Avoid them if you can, because they have side effects. You mix the iterating stuff and the business logic. But instead, you can use one of these three functions, but others in the standard library and in other library we'll see a bit later. So if you want to apply a transformation to every element of an array, but you want to keep their order and the number of elements, you use map. If you want to remove some elements while keeping the value of the others and their order too, you use filter. And if you want to go through an array and build another data structure, you can use fold or reduce. I put two names because depending on the language, they have different names. So the funny thing is that the map and filter kind of keep the spine of the data structure, while the third one would destroy it and let you do whatever you want. If for every element you want to create a list, and for every element you would insert 2 elements in the new list, you can do it. It's possible with fold. So it's quite flexible. The third concept is lazy evaluation. So lazy evaluation, I could define this with giving you the Wikipedia definition or whatever, but it's important to think first about evaluation strategy, because lazy evaluation is one answer to those questions. And those questions are, when do we want to evaluate the argument of a function call, and what kind of value would be passed to this function. So here in the example, I'm calling a function my function, which would take a string as argument. But instead of giving it a literal string, I'm giving it something that would evaluate to a string. So the lower of whatever would lowercase this, and we would get a string. But the question is how to evaluate that. When do we want to evaluate the lower function? And what would be passed to the implementation of my function? So there are several answers to that. The first is strict evaluation, which is also called with other names, as you can see. But the important stuff here is that we will evaluate as soon as possible, which means when given something like that, the lower of whatever would be evaluated, and then we would evaluate my function in that order. And depending of those evaluation strategy called by value, by reference, or by sharing, or there are others, we would not give the same exactly to the body of the function. In the first call by value, we copy the arguments and give them to the body. So if the body does anything with them and change them or whatever, it doesn't reflect on the outside of the function. With the call by reference, it is different because we are passing references to the values. So if the body of the functions change them, it would be visible from the outside. Remember what I told you about arrays earlier? And the call by sharing is what is taking place in JavaScript, is a mix of both of them. For some kind of value, you do the call by value stuff, and for other kind of values, you do the call by reference. Because it would be too simple, I guess, to have just one strategy. I'll put some example a bit later. About the non-strict evaluation, it's another way of answering the question I was asking earlier. Non-strict evaluation is basically the same as lazy evaluation, so that's it. That's what interests us. There are two kinds I will present today. The first is call by name, which in this case, we are not going to evaluate the lower stuff here. We are going to copy it the whole expression and replace it in the body function wherever we are using the parameter in the body functions. Which means that the lower functions would be only evaluated when needed and not before. And the call by need is exactly the same, except that if we evaluate several times the parameter, we would like cache it to just evaluate it once or never. And in the first case, if you are using it, I don't know, 3 times, we would evaluate it 3 times. So lazy evaluation basically is something to delay the evaluation of an expression until its value is needed. And what's the point? The point is that we get free optimization in many cases because we can avoid useless computations. Indeed, you don't need to evaluate the lower stuff if you actually don't use that parameter, or if you don't use it, you don't even need to evaluate it to get a function, a value, and then not using it. Also about the maintainability, I put 2 examples of what you can do which are funny, like you can express infinite data structure and stuff, but I'm not going to, I'm running out of time. So the point is I'm giving an example which is really better. So we are talking about Lodash. It is a library in JavaScript which gives us an API to manipulate collections. And it is lazy since a few years ago. So with that example, I've got a list of integers. I've got a function add1 that would just take a number and add 1. And also you can see I'm doing console log stuff to just see what is executed and when. And also, if the number is superior to 2, I'm just saying that it would be slow. For example, let's imagine it would be slow. So I'm printing slow. And I've got another function which is called isSmall, and it returns true if the number which is given to it is smaller than 3. And also, we do the console log stuff. So first example with the JavaScript standard API. I've got my list. I use map to add 1 to every element. I use filter to only keep the small elements. And then I use slice to keep the 2 results in the end. So you see, I'm doing the map, and then the filter, and then I've got my result. With Lodash, I'm basically doing the same, except I have to wrap my list in a Lodash structure before. And also the slice method is called take here because I just need to take 2 elements. And you see, I don't need to execute the useless stuff because here we had to map to every element, including those we were throwing away. So it's not the case here because of lazy evaluation, and I still can express my computation exactly the same way. I'm not like doing optimization in my code. So with an animated picture, you can see without Lodash, I'm doing, see, it's another example. I have to filter and then I take. So basically, I'm doing more computation than needed. And with Lodash, I stop when I've taken 3 elements, which is in this example what I need. So with lazy evaluation, I can separate the definition of computation and the execution of them. So you can see it as a kind of glue that allows you to assemble pieces of program without sacrificing the efficiency. Like the pipe in Unix commands, you can have some kind of stream and have data from one part of the program to another part of the program, but still you don't have to do the steps like one by one. You can have a flow. So it's nice because your code would be, you have better maintainability and readability of it, and also the performances are not always bad. But you have to know that it can introduce some overhead, but it mainly depends on the technologies, like in JavaScript or Haskell, or it's they are not optimized the same way. The last stuff is immutability. We call an immutable object an object that can't be modified after it was created. So it's basically like a constant in some languages. So in JavaScript, some types are immutable by default. You can see here I'm doing n equals 10, but if I do n equals 10 plus 1, I'm not changing 10, I'm not changing 1, I'm just creating a new value. I'm changing the reference here, which is n, but I'm not changing the values because it's numbers. But with objects and arrays, because arrays are objects in JavaScript, it's not the same. You see, I'm creating an object. I'm creating a kind of copy of this object using a variable called alias. And then I'm using object.a equals 2 to change the first object. You can see if I display the first object, it has changed, as expected. But if I display the second, which was a copy, it has also changed, because I mutated the object, and alias was just a reference to the same object. It was not a copy. So it's not immutable. Side note, const, which was introduced recently in JavaScript, does not help with that. It only ensures that you are not modifying the references, but this example does not change the references. It changes the inner object. So it's not a solution here. But there is a library called immutable.js, which was developed by Facebook. And it gives us an API to manipulate immutable collections, such as lists, which are kind of like arrays, or maps, which are kind of like objects, but many others. Quick example, you can see here I'm creating a map by giving it an object. So a map is basically a key value stuff, key value collection. And I'm creating a second map by just modifying the first. I'm telling the program I just want to change one value, and it gives me another map. But the first has not changed. As you can see, when I say get, I still got 2 and not 50. Also, I can compare them. And this example is about the map data structure, which is not the same as the map function. But the point here is that if I use immutability, I got one value per reference, which is really nice to think about your program. I got no side effects, and so it's basically for free. It's thread safe on this behavior. But you could tell, okay, but we are like copying values here. So what about the performances? The memory consumption, and sometimes it depends on the runtime. It introduces overhead, but not that much. As you can see here, you've got a tree, the black one on the left, and I want to add a new element after the F node. I don't have to copy the whole tree. I just copy the root element and reference all the elements if it's the same, but I have to create new nodes if they have changed because they have more references or different values. So basically, I'm reusing the old stuff and mixing the new with the old stuff, which would be dangerous if I could modify the old stuff. But as I said, it's immutable, so there is no chance I could modify the black stuff. So I can reference it from a new data structure without doing like race conditions or horrible stuff like that. So a bit of advice, use const whenever you can, because it's nice, and also in JavaScript, when you're writing your programs, it's quite rare to have the need to change a reference. With const, you ensure that you won't change it, so it's more readable. The reader can do this hypothesis that you won't change the reference. Also use let if you can, because it's better than var. But the really important stuff is the second one. When you're creating API or using them, try to do them in an immutable way. Like, if you need to modify something, just return new stuff and don't touch the original stuff, because it causes side effects like this. We've got the push function on arrays in JavaScript. It just returns nothing and changes the array. So it's like the code which would be before would not be the same as the code which would be after. If you put the same code after and before, it would not have the same result because the order would be important. If you have an immutable API, it's more like expressions. So you don't really care about the order of the statements because there are no statements. So that's it. Sorry, I had to speed up a bit at the end. There are 3 references here that are really interesting. The first is an academic paper, Why Functional Programming Matters, which explains how higher order functions and lazy evaluations are nice to write functional programs, and why this is important. You can just read the abstract, introduction, and conclusion, and that's it. It gave you a strong idea of what it is. The examples are quite difficult, but you don't have to read them. It's an academic paper. You can just read the intro and the conclusion. The second is a book which explains more those kind of concepts with playing with function in JavaScript. And the last one is an article about F#, but it applies to every language, to think about the predictability of your language. Like when you are reading it, you don't want to be surprised. Because if you are surprised while reading it, you won't see the bugs. But if the language allows you to, like, if the language doesn't allow you to do that and is tricky, and you've got side effects everywhere, you've got bugs everywhere. Quite the same stuff. So thank you for your attention. If you have, I don't know if we have time for questions. Not really. Well, thank you. I'll be there for today and tomorrow too, so you can just come talk to me, and if you have questions, I'll answer them. Thank you.